Hello, Chemie friends. I wanted to give us a nice video to catch us up on what we need for the homework in this coming week. I apologize. I had to miss class this morning. I wasn't feeling that well. But I'm feeling well enough to talk about some of my favorite things in the space of thermodynamics, so let's go. Where we've been up to this point is we've been doing energy and entropy balances, as you can see here, and we've done them for particular unit operations like a pump, and we've done them for entire systems like a refrigerator. And we've done it specifically if we have access to an ideal gas, because we know the equations for this, water, because we have access to the steam tables, or refrigerants, because we can read those graphs. But you know, most of the world is not those things. So going forward, we need to be able to describe everything else, like all the other stuff that the world is made out of that isn't ideal gas, water, and R134a. So what are we going to do? Well, we need to find something or a suite of some things that can give us three different pieces of information. First up, we need something that can tell us physical properties. So for example, right now I could go to the steam table, and if I know T and P, I can find the volume or the density for water in those conditions. So we want to be able to do that exact same thing for other stuff. And then, as we talked about in class last time, we need to get derived properties, these fancy things like enthalpy, internal energy, Gibbs free energy, entropy, that you can't just get by a measurement. So hugs, we need hugs. Yes, we do. And those, we're going to need equations to get those. And then finally, something that hasn't come up a whole lot yet, but we started to look at it with the refrigerants, we really need to know when different chemicals are going to change phase. Like, what's the boiling point of this? So those are the three things we're going to need to be able to calculate. So how can we find what we want? Well, there's two main approaches. First up is we can go to a lab and we can measure it if it's something that's measurable. Like if we want to know the boiling point of some stuff, we take that stuff, we bring it in the lab, we stick it in a machine, we boil it, and we write down under what conditions that happened. That's not, well, that's always the best way. That's why I put it in this nice little yellow halo. It always is the right answer. The problem is that can be an expensive thing to get. We can't always do that experiment easily. We don't always have the equipment, and maybe we need to know it for a lot of different materials, and so it would take a long time. So, as an approximation to that, we use something called an equation of state. And later on, we're going to use something even better called an activity model, but we're not quite there yet. So we're going to start with an equation of state. And what an equation of state does is it relates things that we can measure, like temperature and pressure, to things we want to know, such as the density. And then through derived relationships, we can go ahead and get things like the enthalpy. So an equation of state can do quite a lot of what we want. It can even help us figure out the boiling point of something. So this is a lovely, sparkly thing, and we're going to start using those today. And equations of state come in three flavors, A, B, and C: empirical, semi-empirical, and theoretical. And empirical means it's a curve fit. Someone went and got some data, they threw a curve on it, and it fits it really well, but it doesn't actually tell you how the world works. It just does an accurate description of a little piece of the data. And you've used one like this before called the Antoine equation, and we're going to be using that again. But that doesn't answer everything. Semi-empirical and theoretical use some theory. So based on like the physics of how the world works, we take some data about this chemical, and then we use it to describe its behavior in other circumstances. And this would be stuff like the van der Waals equation, which your textbook talks a bit about, SRK, which you had used before in KEG 200, and the Peng Robinson equation, which we will be using shortly. So even though this is a video, I do have two problems I want you to work on, and here's what they are. First, I want you to do a thought experiment about what's the worst assumption that goes into the ideal gas law, and why is it the worst? And then I want you to use an actual equation of state to do some calculations. So let's talk about the ideal gas law first. And what's the worst thing about the ideal gas law? Hi there. And something you might note about the ideal gas law is it's both kind of empirical. That is, we got the ideal gas law, we got PV equals nRT from a bunch of people doing experiments over and over where they said, hey, look, if I hold the volume constant and I increase the pressure, something happens with the temperature. Like, that was an observation, so that's kind of empirical. But at the same time, you can get the ideal gas law from first principles. You can look at a collection of molecules and integrate that behavior from tiny little collections of molecules up to moles of molecules, and you land at the ideal gas law. If you go to graduate school, you will probably do that derivation. It's something that happens fairly early on in a statistical mechanics class. Let me get that marker off my face. There we go. So, what are the assumptions that are baked into the ideal gas law if you're deriving it from first principles? I'm going to give you a moment and ask you to think about that, write it down for yourself, and I'll write down a few while we're hitting pause here. Okay, did you come up with any? I have noted down 4 that are the core assumptions that have to do with the ideal gas law. One is that all the molecules you're working with can be best represented by tiny little hard spheres. And what I mean by hard spheres is, well, in fact, more than that, they have no volume, really, to speak of. They are point particles, but they're still round, but they're point particles. And if they bounce off of anything, which, well, they can't bounce off of each other, but they can bounce off of walls, that's a totally elastic collision. And finally, this last point here, non-interacting, that means that they don't attract each other, they don't repel each other, they just, they don't even know. And one ideal gas molecule, a whole mole of ideal gas molecules, can't tell the difference. So which of these, hit pause and ponder, come back ready to discuss, which of these is the assumption that most often fails in real life? Like, why is it the ideal gas law doesn't describe everything? All right, hit pause, go. Okay, you've had a moment to think about that, I hope. What do you think is the worst assumption? And all of these are assumptions, right? So all of these, at some point, fail. Not everything has elastic collisions, but that's pretty good. Most molecules are not point particles, especially when you get into things that are like proteins or polymers. They are very, very much not point particles. So that's a big failing why you can't use the ideal gas law to describe, for example, polyethylene. But really, the worst possible thing going on here is this one, non-interacting. And why is that so bad? Well, you need intermolecular interactions to have stuff change phase. Things that never interact will always stay a gas. That's why ideal gas law can't be used to predict boiling points. But as you know, like water condenses, ethanol condenses, lots of other things have phases other than just straight up gas. And so that's our most common reason that we got to ditch the ideal gas law and go after something more sophisticated. Make sense? Even helium, which is very non-interactive, will eventually condense if you get it cold enough. Okay, our second problem of the day is for you to get comfortable using an equation of state. An example equation of state that's pretty good and yet pretty easy to use, relatively speaking, is the Peng Robinson equation of state. And there's more equations of state for you to choose from in your textbook. But I like this one because there's a really handy calculator we can use for it, and it captures a pretty wide range of materials. So here is the Peng Robinson equation of state as published by our friends at the United States Geological Survey. So I grabbed it off the web here. You can see the equation that goes with this, and there's a lot in there. It doesn't look that easy to implement, but really it's not so bad. It has, as the ideal gas law does, P and V and T in it, and the V is V per mole or V per kilogram, so that works the N into it. It has some constants, and these constants are slightly empirically based. That is, the critical temperature and pressure along with what's called the eccentric factor. That's this little thing called omega that you see right over here. Those are measured values, but the rest of this is just prediction. And so it's not so bad to use. And it's not fun to solve, however. Like this is just pure straight up an equation. I'm giving you the equation. There's no mystery in this equation. And you plug some numbers in and you chug some values out. But because you can see that the volume term is squared down on the bottom here, it makes it not trivial to solve. It's solvable, but it's not trivial to solve. And because I am more interested in you interpreting the results you get from an equation than in you wrestling with algebra, I'm giving you a calculator that does this equation. And your textbook has some suggested calculators that do other equations. And of course, the only thing HISIS actually is a calculator that runs equations kind of like this. So you have lots of ways to phrase a question of one of these equations without you having to spend half an hour wrestling this thing into your calculator. So we're going to do that. So let me show you what we're going to use. It is a spreadsheet, and keep in mind, it's not magic. It is just a calculator for this particular equation. And this spreadsheet is named Peng Robinson EOS, so PREOS.XLS. And you can get it by going to our class Moodle, and then download the software that goes with the old book, downloading that whole set of Excel files, and you'll find this file in there. You'll want this one, and then you'll want another awesome one that's like properties. There's also a steam table one you can use if you like. And the properties one just is a collection of lots of values of critical temperature, critical pressure, omega, and the ABCDs for heat capacity. So hit pause, go off and download that. You're going to need Excel. It does not open well. Well, it opens okay actually nowadays on Google Sheets, but it doesn't open in Apple Numbers. So it works best in Excel. So grab that, download it, take a look, and then unpause, and I'll talk you through how we use it for the rest of this video. Okay, here's a screenshot from Peng Robinson Equation of State, the Excel file. And you, when you have that open, you're going to want to go to the tab labeled Props. That's the one we will use most often. So have that open. And I'm going to give you just a quick tour of what's here and what you need to do to use this calculator. So you are going to want to feed to this calculator everything that is in blue. So you see up here we have a lot of text that's in blue. Those are the things you can change and will be changing. Okay, so for our problem of the day, I want you to figure out the volume at 273 in 1 atmosphere of methane. And so how would you do this? Well, you've got to go look up for methane. So I suggest you type the word methane in here. And you want the critical temperature, the critical pressure, the omega, and the heat capacity ABCD for methane. And you can find that for a bunch of chemicals out here in these last tabs where they have reference materials. And you can copy them and bring them in, or you can look them up in the NIST web book or in the appendix at the end of our book. You can find this stuff in a lot of places. But you have to update these values to be about the chemical that's of interest. And then once you've done that, you can type in a temperature and a pressure, and then lo and behold, look over here where I am circling, you will find values for all sorts of things that we want to know. You can find Z, which is the compressibility. We'll talk about that later. You can find volume, which is great. That was what I just asked you for. You can find fugacity, which we're going to be using a lot. You can find enthalpy, internal energy, and entropy. So this is great. Now, a thing you may have noticed is there's multiple values for each of those things. In fact, sometimes you just get one answer for those things. That's down here where it currently says num. So I don't have one answer for that. And sometimes you get 3 answers for everything. That's because this is a cubic equation, so there's 3 what they call roots. We have 3 answers every time we ask. When you only have 1 root, that means 2 of your answers were imaginary, and we know they're not true. And you say, okay, that's great. I see that there are 3 different volumes shown here for your example, which is propane, by the way, not methane, so you should be changing it to methane. How do I know which one's the right one? Well, in general, when you are working on this first part of our problem of the day, your volume that you want is what's called the stable root. It's the one that goes with the lowest fugacity. So if you look at the fugacity column, which is right here, and you see that this upper root has a fugacity of 0.4, and this lower one has a fugacity of 0.19, that means that the stable answer is everything in this bottom row. So all of these are what's the true answer in this circumstance. And again, remember, not magic, this is just a calculator. But you need some judgment to use your calculator. So you should go set this up and go solve that first problem. But I want to talk a little bit more, just quickly, about the second problem. How do you find the boiling point? Because, my gosh, I have to enter a temperature and a pressure, but you only gave me a pressure. I only know it's 10 bars. How do I find what T that ought to go with? How will I know I'm right? How you'll know you're right is that at phase equilibrium, so at equilibrium, the fugacity of a vapor has to equal the fugacity of the liquid. That's got to be true at equilibrium. So, what do? Well, you look here where you see that this is calculating fugacity for you, and you type in the pressure that you know, the pressure that you want, and then you change the temperature until you see that these 2 values are the same. And then you'll know that the fugacity of the vapor is equal to the fugacity of the liquid, and that will be your boiling temperature. If you feel like being a little sophisticated and are using Excel, you can use the tool called GoalSeek to do this. You see down here there's something called fug ratio. That's just the ratio of these 2 numbers. And so when that's 1, that means they are equal, right? That's the only way for that to be 1. And so you could GoalSeek changing, for example, the temperature until the fugacity ratio equals 1. Or to get used to it the first time through, I recommend you kind of doing the whole guess and check version where you just type in a few temperatures and you see what happens. Okay, that being said, once you can do these 2 things and make this work for different chemicals, you are now well positioned to be able to do the homework and to be able to wander with me out into this wonderful world where we are no longer constrained by ideal gases or steam or refrigerants. Yay! See you soon.